All right, I see that it's time for me to start. So that's exactly what I'm going to do. So first of all, welcome and thank you so much for joining. I know that it's the last session of the day. So if there's any attention left, then please do give it. But I'm very thankful for you joining. So today, first of all, my name is Victor. I'm an evangelist at ClearML. We're an open source MLOps company. And today I'm going to talk about the importance of experiment tracking and data traceability, two things that are in general in finance and insurance very important or very interesting to talk about, but also in general machine learning. If you're any kind of practitioner, data analyst, business analyst, or ML engineer, it's a very interesting set of tools to start to work with or to learn how to work with. So first of all, allow me to set the scene a little bit. I've taken a look at the talks, and I think there is a talk at this point going about responsible AI in finance, and there's more of these kind of topics coming up every day. So especially in the medical field and the insurance field and in the finance fields, it's all about fairness and explainability, right? This is obviously not the only thing that traceability or data traceability and experiment tracking can help, but it's definitely two pillars that are important that we should be focusing on and that receive quite a bit of attention these days. So I wanted to put it a little bit into context. Like you have the fairness pillar. We want not to have as much bias in there as we can. And there's mainly, and I think this for insurance is mainly the important one, is explainability. Like if a model makes a decision for a specific part of the pipeline or for a specific business process, we should also know why it made that decision, right? We should be able to not have a black box of a model, but also to know why it did something, why it does the prediction that it did. And so these two things are, again, being talked about quite a lot, but they're as a thing on their own on the very back end of the system. Like you make the whole model, and then the explainability and the fairness come at the end, right? And then traceability is actually the part where we ask the question, what went wrong? So imagine if in a certain way, explainability or the explainable AI module of your system comes out with a wrong prediction or has like a very weird explanation, or you found new kinds of data that are suddenly not like they used to anymore, or like you have some kind of drift or other type of things. And then their traceability comes back into play, where you want to be able to trace back to, okay, this went wrong, but where did it go wrong? Like what specific part did we do wrong? Where can we do better? Could we spotted this earlier? And so on and so on. So this is essentially where traceability is placed in this kind of component overview. So the first thing I'm going to talk about is what exactly do I mean with traceability? And every single machine learning engineer or data scientist knows this graph by heart. It's what you do every day, essentially. But so this is the machine learning workflow, and I'm going to split it up into three parts. We'll be going over the three parts in this session. But essentially, you start by retrieving data. Obviously, you get some data to start working on. It is a data science workflow after all. So then we go into the first part, which is the data processing. So you can see it here, which are the blue boxes. And essentially, you're going to clean and explore the data just to know what you're working with. And then you're going to prepare and transform it so that it can be used by the next stage. And then the next stage is what most of the, what is the most sexy stage, let's say, which is the modeling itself. And in most importantly, developing and training the model. So this is what most people like to do. This is what most people talk about. But then there's also validating and evaluating the model. And this is actually the first stage where fairness issues, explainability issues, but also just normal machine learning problems that are going to be a problem in the real world, this is where they're going to surface first. So this is actually, together with the latter part, the most important, the first time you encounter these type of issues. And then there is a heck of a lot going on before that we just missed before we know that there was an issue. And then there is a third part, of course, which is the deployment, which is then we take the model that we just trained and we then deploy it to production. It could be as an API, it could be as an app, it could be as a web interface, anything that serves the model that you just trained to an end user is deploying to production. And then once it's deployed in production, you also still want to keep track of everything the model does. You want to monitor it, and you want to be able to update it, both the model and the data. And this is also something we're going to talk about, because traceability extends all the way to there. So if you have good monitoring set up there, things like fairness, bias, explainability, but also normal machine learning problems will be able to be caught there if they weren't already caught in the evaluation stage. This graph will stay on the top right of my slides. You'll always see where exactly in the slides we are at this moment. So as you can see here, we're going to start to talk about data traceability. And if you're a machine learning or data science practitioner, this is a use case that you will probably know or have seen before. So what happens most of the time, very general, is you create an initial data set, right? Doesn't really matter what it is. If you want to do anomaly detection, if you want to do time series, doesn't really matter. You always start with an initial data set and you use it for your first analysis. So this is the exploring phase. But then you find some mistakes. Maybe the data wasn't extracted in the right way, or maybe there are data missing and there are somewhere else, or maybe like there could be any type of mistakes. And then we start to ask an intern to actually find out where those things went wrong, and we let them figure that out. But this is now a second person in the process. So now we have data sets, versions that have to be passed from you, the data scientist, to the intern and back, and all the way through. So that intern will then add new data, or fix some data, or remove even some data. And now they will have a new version, and maybe they'll send it through you through a zip file, or maybe they upload it to Google Drive, or if you're lucky, they'll be versioning it using GitHub. But that's not ideal. Like you could say in the zip file case, which zip file was in used data? If you have to go back through Teams and find like the last zip file that your intern sent, it's not ideal. Did it send it over Mail? Did it send it over Teams? The moment multiple persons start to be involved in this process, it gets really, really difficult really quickly. And then more problems start to arise. Who removed the sample that I added before? Where do these other samples come from? Like who added them, and when were they added? Why were they added? This is not the same data. So things like that are becoming an issue quite quickly. And this is the workflow, believe it or not, for a lot of people. Also a lot of clients that we see come in. So it's definitely not weird to see this happen. So what can we do about this, right? So data traceability is the term that can be used to have a set of tools, or to describe a set of tools that actually talks about all of this. So one thing that these tools offer you is Lineage, is what's called Lineage, or genealogy. Essentially, you're creating different versions of your data set, each with their delta over the other. So you can always see in this version, this and this and this data was added, this and this and this data was removed. Here you can see an example in the ClearML interface, where you can see, okay, this is the end data set. The most right is the end data set. It has all of the samples from this sub data set, or parent data set. It has some samples of this parent data set, and that parent data set was based on a previous parent data set. And so you can always, for each step, you can always keep track of how many files were removed, how many files were added, who added which files, when. All of these things are just part of the design. So if you use kind of this tool instead of just zipping it and sending it around, it already saves so many headaches. So this is the first thing that this data traceability can do for you. So you will always know where your samples in your data come from in the end. So you can always trace it back to where they were first added. There is a bonus to that. So now that we already have this dataset version concept that we're using and not the zip file, we can actually attach more info to that version. For example, each version is saved and can have attachments. So in this case, it's saved in the ClearML database, but it could be any other data lineage system, and it can have attachments. So for example, important statistics like class distribution or bias indicators or explainable metrics can be added to the data set. Described metrics, can be added to the data set before it was ever used. And so then you can always go back, search through the versions and see, okay, when we added this change, the graph went all haywire, so this is probably where an issue occurred. So it's a really neat way to keep an overview of your dataset versions without having to look through all of the files. You can save data externally other than on a single laptop. So if you're saving all of your data on a single laptop, it's not ideal. You want to save it somewhere central that you can also share it with different people. But I imagine that you say immediately, like, I'm not sharing this with any Googles or AWSs or whatever, and I would agree. But that's also why there are a lot of open source tools. So as an example, ClearML is an open source tool, so you can use the open source server, run it on your own systems, and then just save all of the dataset version information there. And it's within your own control and your own system. And it also makes, like I said, it makes data versions shareable because now it's a central system. You always know who is accessing it. You can just send a link as well to this specific version, but also people won't be confused on which is the latest version, what should I use. You can use tags and organization stuff as well. So it makes it really, really organized. It's essentially built specifically for this. And just, you can see it as a table, which is different lines, and every line is a version. You can just share that all the way. So that makes it much, much easier to deal with than dealing with zip files, obviously. Now we've arrived at the bottom part, the most sexy part of the whole pipeline, which is the experiment tracking. Experiment tracking is, what I mean is experiment tracking is used on this part of the pipeline, essentially when you're training a model and when you're evaluating the model. And a common use case there is, again, just like the common use case we had with data versioning, is you test multiple different approaches. That's the first thing a data scientist is going to do, is they're going to take different models, different approaches, and just experiment, right? Just test it out. And then what happens is you change a lot of parameters. And most of you will probably use Git already, which is like a code versioning system, but you won't commit or make a new version of every single parameter change you do, because you don't know yet, by definition, you're experimenting, you don't know yet if that's going to be a good change or not. And so you don't want to actually make a version or make a new version of something that you don't know yet that is good. And you end up just changing a lot of parameters and not saving in between. So for example, you forgot to change the output names of plots or model files, which means you overwrote it. And then now you have like the best model that you knew you made at some point, but all the files are garbage and they're all through each other and they've overwritten. So that can happen faster than we think. And then, wait, which parameters were used for this plot again? So you might, even if you have the output name game perfectly fine, which parameters were used? Like which code was used? How can I reproduce this specific plot, even if I changed a lot of stuff since then? Maybe not, probably not. So, oh crap, where did I save my best model, right? It's things like this that make it, yeah, it's things like this that we encounter if we don't take proper care of tracking our experiments, our experimentation phase. And just to set the scene a little bit on what I mean with that, is that I mentioned code already. You probably version your code in Git or something similar. And we also talked about data versioning as well. So where does an experiment lie in between there? And so the idea of an experiment is that it is a single run of your code. So of the code that is at that current moment. Like I said, you're not going to commit every single parameter change you do. So that is what experiments do. The experiment is a single run with a single set of parameters, with a single type of code. And so your code stays the same, your parameters, but this also includes things like outputs, plots, artifacts, model files, things like that, because they are not part of the code. They get created by the code by a single run of your code. And if you change something slight in the code, all of those outputs will change as well. Console logs, for example, everything that is printed to console or to the output of your Jupyter notebook will also have to be logged. And then a very important one is environment details. So things like Python packages, things like Docker containers, things like operating system details and stuff like this that will allow you to later be able to reproduce the exact same environment, so that if you rerun your code with all the changes that you did, you will get the exact same plots, model files, and everything else. Plus, and this is where the two start to work together, you can add a reference to the dataset version. So if you had a specific, if you have your dataset versioning, it's very easy to say this whole training run, this whole model was trained on that specific data. And then it's very easy to go into the history of your dataset and look at exactly what was in the dataset at that point in time. And just to make it a little bit more practical, how can you actually add it? And it's super, super easy. So it should never be a barrier for you to add this kind of thing to your code, because all you need to do, and this is an example again for ClearML, but a lot of other tools are out there. You can definitely search for the other ones as well. And most of them use only a few lines of code. So adding these 2 lines will already log all your console output, all your hyperparameters, all your plots and model files and whatever. So you can just add these 2 lines and just forget about it. And then just do your experimentation, and your future self will thank you if you do this well. And then a final part that I want to touch on in this particular part of the diagram is reproducibility. So reproducibility becomes very, very important if you're trying to post-mortem figure something out, but also if you're experimenting very, very quickly and very heavily, you want to be able to show your team or your share or stakeholders that you can actually do it. Like, you know the exact code that was used to do this specific thing, and other people should be able to do the same. So you can reproduce any experiment to get the exact same findings. That's the point of reproducibility. And what we don't want is this specific person that knows exactly on the 17th cell of this Jupyter notebook, you have to set try new it to false, and then it will work. And then you have this only one person with all of the knowledge. That's not something you ideally want in a good team. And so it's important that other researchers or other colleagues can confirm your findings and double check to make sure there are no mistakes are made. And even for yourself, if reporting time is there, you can just easily recreate the plots as it were from back then, and never be fearful that you will lose your model output to add it to your PowerPoint slides or whatever. And then reproducibility also helps root cause analysis, because once you find a specific reason that something went wrong, or explainability has shown that there is something wrong with the model, then you should be able to trace it all the way back to this experiment. And then if this experiment wasn't the reason, because you can compare it to different other experiments, then you already know it's somewhere in the data or it's somewhere in the deployment. So that makes it a lot easier with the root cause analysis as well. And I mentioned comparing. Comparing is one of the most powerful features you have once you start tracking these experiments very well. So once you do this very well. And in this case, for example, this is an example where you can compare 3 different runs of your code, and then you have the uncommitted changes highlighted, you have the commit ID, which is different, you have different packages installed in the most right one. So all of these things make it very easy to see what happened. And for example, here, the base learning rate, for example, wasn't available here because it was like an earlier version of the model, and then we added that later. So if there were any other changes, you could see that here very, very quickly. And then a final one is the metrics that we're searching for. In this one, it's F1 score, but it could be anything that you're looking for. In this case, you can also even compare them on graphs together. So it's very, very easy to find the best model. If you forgot, for example, what the best model was, you just select them all, select compare, and you can just find the highest graph. It was that one. Go to that experiment, reproduce it, get all the plots, get all the output. Very, very useful, both in root cause analysis as well as reporting. And then remote execution. So remote execution is something that not a lot of people put a lot of time in, but it's so valuable. And especially, I think, in the finance sector, there's much more security there. So usually it's actually something you have to do because you can't just run on the data on your local machine. And so the idea there is that if you're working on your local machine on dummy data and you already have the experiment that you run on the previous data, the experiment is now completely reproducible, right? Because you know the environment, you know the packages that were installed, you know the exact code that was used to train all of it. So imagine that you develop on this dummy data, and then you can reproduce the exact code, but this time you can do it on real data on another machine. So you just say to the machine, like, clone my repository here, or clone my experiment here, and then run it on the data that you have on your machine that I don't have access to. And then you could be getting anonymized metrics, for example, the metrics that we saw before, the F1 score or any accuracy score that might be interesting, without ever having seen the real data. So this reproducibility could be more important for these kinds of approaches, but it's also just very, very nice to have. So it opens a whole lot of doors. And then there is the final part, the left part of the diagram, so the model deployment. And again, I'm going to start with a common use case, as a use case that we see all the time. And I was an ML engineer for 3.5 years. I've struggled through this my fair bit. And then you start with like, okay, we get the best trained model from the experiment, right? We have the experimentation done. It's all in like a folder or whatever with a different name. And I just get the best trained model from my previous experiments. And then I want to make it accessible by an application, right? Either via API or web interface or whatever. But wait, the model that I just deployed, was it version 5 or version 6? Like it doesn't have that in the name. It was just a timestamp, for example. And then was this the model that was trained on the new data that we just talked about, or was this not? And by now the code has changed, so I can't really do it anymore. And then, yeah, it gets really messy again because you don't have this overview. And then why is this model acting strange on this particular client, right? So it could be all kinds of things. And at that moment, you're in the dark. So what you want to do is to be able to find this upfront, to find this early, and start with deployment monitoring and have traceability all the way back. So, for example, you could check for anomalies like drift detection. You could check for anomalies, and for example, for drift detection, you can generate a lot of statistics based on the model that the model outputs, and then send that back, have different dashboards on that, and then that will trigger when something goes wrong. But if you track the model statistics, you have to also make sure that they're not out of spec when compared to when it was trained. But what was the data that it was trained on, right? So to be able to know this, you can dynamically link it to the experiment that was used to create the model, right? Because everything is connected. And then model traceability, so each model that was deployed is directly traceable to the original code and the original data was used. And that actually has an additional benefit in that it is less work for the data scientists to get things into production, because when they're running their experiments as part of the tracking that we just talked about in the previous part of the diagram, it's very, very handy that it already also saves all of the model files, right, as part of your experiment tracking. But what that means is that while you're experimenting, you're actually building up a model repository, because you all have the models from every single experiment run. And then it makes it very easy, because then now you can just tag a specific model as this was the best, this is probably good for production or at least for testing. And then you just use that tag to then deploy that model. And that model is still connected to the original experiment, which is connected to the original data. So everything is connected by that. You have no gaps. There is nowhere where you have to copy and paste files or like put it into another workflow or whatever. That's what I was talking about. So the model repository, the models are captured by the experiment tracker. Now you have everything in a list, and it is completely traceable. So this is what something like that might look like, is that you have the overview, all of your experiments, and then all of the models that those experiments made. And then you can publish it or give it a tag to be able to pick up and then just serve that model immediately, and you know exactly what the code was that was used. Right. I hope I didn't bore you too much at this end of the day. So a quick recap. Essentially what the value is here is that if you have these kinds of models running, you have all your explainability in place. Even then, things might go wrong. Even if you don't have any explainability at all, machine learning will go wrong. And then it's always so valuable, always so easy to then go back and then go through the ML model that was deployed, connected to the experiment that was used to train it, which is connected to the dataset version. And it makes it very easy to switch over or to make a new version to fix certain issues that you might be having. So that's the message I want to end with, is traceability can really save you a lot of time, but it can also make your ML systems just a little better, because it allows you to figure out what went wrong a lot easier. All right, so thank you so much for paying attention. If there's any questions, feel free to drop them in the chat. These are all of the links and connection points you have to ClearML. We are open source, so like I said before, there is no reason not to try it. It's completely free, and if you want to run it on your own servers, you can always do that. If there's any questions or problems that you face while you try it out, essentially, you can go to our Slack channel, clearml.slack.com, or via our website, and there will be plenty of people there that are willing to help you out. So yeah, feel free to try it, and thank you for watching. I see that there is no questions in the chat, so I think I'm going to end it here. Feel free to ping me on Twitter or send an email at victor.sunk, which is my name on the screen right now, at clear.ml. Sorry. So if you just want to send in a quick email, you can also just find me on LinkedIn under the same name. Can folks connect with you in June as well? Yeah, I think you're mentioning the MLOPS World Summit. If you are, yes, we will definitely be there. Our CEO will be doing a talk there, and I will be giving a virtual workshop on how to use the tool. So feel free to drop in there as well. Okay, if there's no more further questions, I will end the stream here, and thank you again for watching.